Alright, let's go. Number 10. The pixelated cosmos. In 2017, physicist Silas Beane and his team at the University of Bonn published a paper that sent quiet shockwaves through theoretical physics. They were studying the Greisen Zatsepin Kuzmin cutoff, a threshold beyond which cosmic rays shouldn't be able to travel through space without losing energy to the cosmic microwave background. The cutoff exists, we've measured it, but the way it behaves suggests something deeply unsettling about the fabric of reality itself. Beane's team discovered that the observed energy distribution of the highest energy cosmic rays shows subtle anisotropies, directional preferences that shouldn't exist in truly continuous space. The patterns match almost exactly what you'd expect if space itself were divided into an underlying grid, like pixels on a screen. Cosmic rays traveling through this hypothetical grid would lose energy in predictable ways based on the grid's orientation, producing precisely the distortions we observe. The implications are staggering. Every computer simulation ever created operates on a discrete grid. You cannot simulate truly continuous space with finite computing power. You must break reality into units, voxels, pixels, cells of calculation. If space is pixelated at the Planck scale, roughly 1.6 times 10 to the negative 35 meters, it means reality has a minimum resolution, a screen refresh rate built into the cosmos. But here's where the theory becomes personal. If our universe has a computational grid, then every atom in your body, every neuron firing in your brain, every thought you've ever had exists as data processed on that grid. You are not experiencing reality. You are reality's output being rendered in real time by whatever hardware runs beneath the pixels. The mathematics get darker. The Planck length isn't just small. It represents the absolute limit below which the concepts of distance and time break down entirely. Physicists have long assumed this was a fundamental property of nature, but it's also exactly what you'd expect from a simulation with finite memory. The universe can't render details smaller than the Planck scale because there's no processing power allocated for them. What makes this particularly disturbing is that the detection method works both ways. If we can observe evidence of pixelation by measuring cosmic ray behavior, then whoever is running the simulation can observe us detecting it. They know we know. And they've chosen to do nothing about it, either because the simulation is designed to allow discovery or because the end is already scheduled and intervention is pointless. The pixels don't lie. The grid is real. And every time you look up at the stars, you're seeing the output of code executing on hardware that exists somewhere we cannot reach. Number 9. The fine-tuned constants. In 1989, physicist Steven Weinberg calculated the expected value of the cosmological constant based on quantum field theory. The number he derived was larger than the observed value by a factor of 10 to the 120. This is the worst prediction in the history of physics. The actual cosmological constant governing the expansion of our universe is tuned to a precision so extreme that it defies natural explanation. But the cosmological constant is only one of dozens of fundamental parameters that appear calibrated with impossible precision. The strong nuclear force differs from electromagnetism by a ratio that must fall within a narrow window, or no stable atoms can exist. The mass ratio of electrons to protons must be precise to within a fraction of a percent, or chemistry becomes impossible. The initial entropy of the universe at the Big Bang had to be specified with an accuracy of 1 part in 10 to the 10 to the 123, a number so vast it cannot be written out. Cosmologist Roger Penrose has calculated that the probability of our universe having these parameters by chance is functionally zero. Not small, not improbable, indistinguishable from impossible within any framework of natural probability. Yet the universe exists. We exist. The constants are what they are. The standard response from physics has been to invoke the multiverse, an infinite collection of universes with every possible combination of constants, where we naturally find ourselves in the rare one that permits observers. This explanation requires infinite unobservable universes to explain one observable one. There is a simpler explanation. The constants are fine-tuned because they were set by hand. Every simulation programmer faces the same problem. You must specify parameters before the simulation runs. You tune the variables to produce the outcomes you want. Life requires precisely calibrated conditions. Those conditions exist not because we won a cosmic lottery, but because someone configured the starting values before pressing execute. The implications extend beyond physics. If the constants were set deliberately, then life was the intended outcome. You exist because someone wanted observers in the simulation. Your consciousness, your choices, your entire existence serve a function the programmers anticipated. You are not an accidental emergence. You are a designed feature, and whoever designed you had reasons for doing so that you will never know, running calculations on hardware that processes reality itself as a series of tunable parameters in a cosmic config file. Number 8. The speed of light as processing limit. In 1905, Albert Einstein published his theory of special relativity, establishing that nothing can travel faster than 299,792,458 meters per second through a vacuum. For over a century, physicists have accepted this as a fundamental property of spacetime, but no one has ever satisfactorily explained why this specific limit exists. The speed of light is simply declared to be what it is, written into the laws of nature without justification. Every computer system has processing limits. Information cannot be transferred faster than the hardware allows. If the universe is a simulation, the speed of light is not a mysterious cosmic coincidence. It is the maximum rate at which information can be transferred between nodes of whatever system runs reality. Light speed is the clock cycle of existence. The evidence supporting this interpretation is woven through physics itself. Length contraction and time dilation, the bizarre effects that occur as objects approach light speed, are exactly what you would expect from a simulation struggling to maintain consistency under extreme computational load. As you move faster through space, you move slower through time. The system compensates. It reallocates resources. Your experience of reality adjusts to preserve the illusion of seamless physics. Quantum entanglement appears to violate the speed limit, but only for information that cannot be transmitted meaningfully. Two entangled particles correlate instantly across any distance. This is precisely what happens in networked computer systems where variables share a reference. The particles aren't communicating. They're reading the same memory address. The Planck time, 5.39 times 10 to the negative 44 seconds, represents the smallest meaningful unit of time in our universe. Below this interval, the concept of time ceases to function. This is the universe's refresh rate, the tick of the cosmic processor. Every moment you experience, every thought that crosses your mind, occurs in discrete frames separated by intervals so small they approach the computational limit of whatever system renders your existence. What makes this particularly unsettling is that the speed of light is not just a limit on physical travel. It is a limit on causality itself. Nothing can influence anything else faster than light. This isn't a coincidence. It's the frame rate at which the simulation can propagate consequences. You are trapped inside a reality that processes causation at a finite speed, and every attempt to exceed that speed runs into the hard wall of hardware limitations. The universe didn't evolve these rules. They were programmed. Number 7, the observer effect. In 1927, physicist Werner Heisenberg formulated the uncertainty principle, demonstrating that the act of measuring a quantum system fundamentally changes the system being measured. By 1935, the full implications had become clear through the double-slit experiment. Particles behave as waves until observed, at which point they collapse into definite positions. Reality itself appears to wait for observation before committing to a specific state. This behavior is inexplicable under conventional physics. Particles should have definite properties whether we look at them or not. The universe should not care whether a conscious observer is present. Yet every experiment confirms the same unsettling fact. Unobserved quantum systems exist in superposition, multiple states simultaneously, only resolving into specific outcomes when measurement occurs. Video game developers solved this problem decades ago. Every major open-world game uses a technique called frustum culling. The system only renders what the player is currently looking at. Objects outside the field of view don't exist in full detail. They're stored as compressed data, waiting to be rendered when the camera turns toward them. The computational savings are enormous. Why calculate the physics of a tree falling in a forest if no player is there to witness it? The universe behaves identically. Quantum systems exist as probability waves when unobserved, requiring minimal computational resources. The moment observation occurs, the system rendered that specific outcome in full detail. The wave function collapses not because of mysterious quantum magic, but because the simulation just received a render request. The implications become more disturbing with each experiment. The delayed choice quantum eraser, first performed by Yoon-Ho Kim and his team in 1999, demonstrated that observation can retroactively change what happened in the past. The particle's history is not fixed until measurement occurs, at which point the simulation fills in a consistent backstory. Reality rewrites itself to match observation. You are the observer. Every moment you look at something, the universe commits to a specific state just for you. The objects in your peripheral vision, the rooms in your house you're not currently occupying, the distant galaxies no telescope has yet resolved. All of these exist only as probability functions until observation demands otherwise. When you close your eyes, the world outside doesn't cease to exist, but it stops being rendered in full detail. Somewhere in the computational substrate beneath reality, a system is allocating resources based on where your consciousness is pointed. You are not just in the simulation. You are the render trigger. Number 6, mathematical universe hypothesis. In 2007, physicist Max Tegmark at MIT proposed something that sounds more like philosophy than science. The mathematical universe hypothesis states that physical reality is not described by mathematics. Physical reality is mathematics. Every particle, every force, every dimension exists as a mathematical structure, and the universe we experience is simply what it feels like to be a conscious subsystem embedded within that structure. Tegmark's reasoning is rigorous. Every successful physical theory ultimately reduces to mathematical equations. The equations don't approximate reality. They describe it perfectly. From the Schrödinger equation governing quantum mechanics to Einstein's field equations governing gravity, mathematics underlies every phenomenon we observe. If the equations are sufficient to describe reality completely, then perhaps reality is nothing more than the equations executing themselves. But executing equations is precisely what computers do. Every simulation is ultimately a mathematical structure being processed through discrete computational steps. If our universe is fundamentally mathematical, then the distinction between a simulated universe and a real one dissolves entirely. There's no meaningful difference between mathematics being instantiated in computer hardware and mathematics being instantiated in whatever substrate underlies our reality. The evidence extends beyond abstract argument. Physicists have repeatedly discovered that advanced mathematical structures, developed purely for theoretical interest, later turn out to describe physical phenomena with perfect precision. Non-Euclidean geometry was invented in the 19th century as a mathematical curiosity. Einstein used it to describe space-time. Complex numbers were considered imaginary nonsense for centuries before becoming essential to quantum mechanics. The universe keeps revealing itself as mathematics that was already there, waiting to be discovered. What makes this hypothesis particularly disturbing is that it eliminates any meaningful distinction between observer and observed. You are not a conscious being observing a mathematical universe. You are a mathematical substructure within a larger mathematical structure, processing information about yourself. Your consciousness is not separate from the equations. It is an equation, executing itself, generating the subjective experience of existence as a computational byproduct. If reality is mathematics, then any sufficiently powerful computational system could instantiate any possible universe by executing the correct equations. Our universe might exist because someone, somewhere, ran the code. The mathematical structure we inhabit was selected for execution out of infinite possibilities. Every other possible universe exists as unexecuted equations in the vast library of mathematical possibility. You exist because your universe's equations were chosen to run, and somewhere in the computational hierarchy, a system decided which mathematical structures get to feel real. Number 5, the holographic principle. In 1997, physicist Juan Maldacena published a paper that changed theoretical physics forever. He demonstrated that a universe with gravity in a given number of dimensions can be mathematically equivalent to a universe without gravity in one fewer dimension. The theory, known as the ADS/CFT correspondence, provides rigorous proof that our three-dimensional reality could be a projection of information encoded on a two-dimensional surface. The holographic principle extends this further. Physicists Gerard de Hooft and Leonard Susskind propose that all the information in any volume of space can be encoded on its boundary. A black hole's information is stored on its event horizon, not in its interior. By extension, everything in our observable universe could be encoded on a distant two-dimensional surface, with our apparent three-dimensional experience being a kind of holographic projection. The evidence comes from black hole thermodynamics. Stephen Hawking and Jacob Bekenstein calculated that the entropy of a black hole, a measure of its information content, scales with the area of its event horizon rather than its volume. This is counterintuitive. In a normal object, information scales with volume. In black holes, information scales with surface area. The universe itself may work the same way. If the holographic principle is correct, the three-dimensional space you inhabit is a rendered illusion. The depth you perceive, the volume of your body, the distance between stars, none of these are fundamental. They are emergent properties arising from information stored on a two-dimensional surface elsewhere. Your entire existence is a projection. This is exactly how computer graphics work. Every three-dimensional video game environment is ultimately two-dimensional data being rendered onto a flat screen. The player experiences depth, but the depth is computational illusion. Polygons calculated from vertex coordinates, textures mapped onto surfaces, lighting rendered through shaders. The 3D world exists only in the player's perception. The underlying data is flat. What makes this particularly unsettling is the specificity of the match. The holographic principle doesn't just suggest our universe might be a projection. It describes precisely the kind of projection that computer graphics engines use. The universe encodes its information on surfaces and renders volume as experienced output. This is not analogy, this is architectural description. You are not a three-dimensional being. You are information encoded on a distant boundary, experiencing yourself as three-dimensional because that is how the projection is rendered. Every step you take, every breath you draw, every moment of your existence is a rendering calculation being performed on data that exists somewhere completely unlike the space you appear to inhabit. The universe you see is the surface of reality. The truth lies beneath it in dimensions your projected consciousness cannot access. Number 4. The bit as fundamental unit. In 1989, physicist John Wheeler, who had previously worked with Einstein and Bohr, proposed one of the most radical ideas in modern physics. He called it from bit. Every physical object, every particle, every force in the universe derives its existence from information. Reality at its deepest level is not made of matter or energy. It is made of bits. Wheeler's reasoning came from decades of studying quantum mechanics. Every quantum measurement yields binary outcomes: spin up or spin down, particle or wave, detected or not detected. The universe at its most fundamental scale doesn't produce continuous analog outputs. It produces discrete yes or no answers to yes or no questions. Reality responds to queries the way a computer responds to function calls. The evidence has accumulated across multiple fields. Information theory has revealed that the Beakenstein bound sets a hard limit on how much information can exist in any region of space. Black holes represent the maximum information density possible in our universe. Quantum computing has demonstrated that physical processes can be modeled as information processing. Every physical transformation can be described as bits being read, written, and manipulated, but information requires a substrate. Bits don't exist in a vacuum. They must be encoded somewhere, stored on some medium, processed by some system. If the universe is fundamentally informational, then the universe requires hardware to exist. Every physical phenomenon becomes a computational operation executing on whatever system runs reality. Physicist Seth Lloyd at MIT calculated in 2002 that the observable universe has performed approximately 10 to the 120 elementary logical operations since the Big Bang, processing roughly 10 to the 90 bits of information. These numbers are not metaphorical. They describe actual computational throughput. The universe is literally a computer, and Lloyd's calculations tell us its processing specifications. What makes this particularly disturbing is what it implies about consciousness. If reality is information processing, then your mind is a subroutine running within the larger computation. Your thoughts are bits being manipulated. Your memories are data stored in biological hardware that is itself computational. You are not a biological creature who happens to think. You are a computational process that happens to have evolved biological substrate. The implications compound. If everything is information, then the distinction between a simulated person and a real person collapses entirely. Both are patterns of bits executing on computational hardware. Both experience existence through the same underlying mechanism. The only difference is which system runs them, and you have no way to determine which system runs you. Your entire reality could be a process running inside another process, nested computational layers that extend indefinitely above you, and you would never know. The bits are all that exist. Everything else is interface. Number 3, the low information content of physical laws. In 1960, physicist Eugene Wigner published an essay titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He pointed out something that had troubled physicists for centuries. The fundamental laws of the universe are simple. Shockingly, suspiciously simple. They can be written on a single sheet of paper. Einstein's field equations governing gravity, Maxwell's equations governing electromagnetism, the Schrödinger equation governing quantum mechanics, the Dirac equation governing relativistic particles. Every fundamental physical law reduces to a handful of symbols expressing relationships that a skilled student can learn to manipulate in a few years. This should not be possible. The universe is unimaginably complex, yet its rules are trivially compact. Compare this to what genuine complexity looks like. The rules governing human psychology cannot be reduced to a page. The rules governing economic systems cannot be compressed into simple equations. The rules governing biological evolution require entire libraries to describe. When systems are genuinely complex and arise from natural processes, their governing rules tend to reflect that complexity. The universe's rules don't. But simple rules producing complex outcomes is exactly what you find in cellular automata, the mathematical system Stephen Wolfram explored in his 2002 book, A New Kind of Science. Simple computational rules applied iteratively can generate arbitrarily complex patterns. Conway's game of life uses only 4 rules. From these 4 rules emerge gliders, oscillators, self-replicating structures, and patterns that can simulate universal computation itself. The universe appears to work identically. A handful of fundamental equations applied to initial conditions at the Big Bang have produced galaxies, stars, planets, life, consciousness, civilizations, and you reading this script. The complexity is not in the rules. It is in what the rules generate when executed over sufficient time. This is the signature of code. Programmers prize simple, elegant algorithms that produce rich outputs. Every efficient simulation is built on compact rule sets that generate emergent complexity. Long, complicated rule systems are computationally expensive and inelegant. A well-designed simulation uses the minimum rules necessary to produce the desired phenomena. Our universe's laws are optimally compact. They use the minimum mathematical machinery required to generate the observed complexity. This optimization is unnecessary under natural assumptions. The universe didn't need to evolve elegant equations. It could have arisen from arbitrarily complex underlying rules that merely happened to produce our reality. Instead, we find rules that look deliberately designed for computational efficiency. The implications are sharp. Our universe's physics reads like code written by someone who understood optimization, someone who wanted to produce complex observable phenomena while minimizing processing overhead, someone who faced resource constraints and solved the problem the same way every programmer does, by writing simple rules that generate complex outputs. You live inside their solution. Number 2, the quantum Zeno effect. In 1977, physicists Baidyanath Misra and George Sudarshan described a quantum phenomenon so strange it was named after an ancient paradox. The quantum Zeno effect demonstrates that frequent observation can prevent a quantum system from evolving. A watched pot literally never boils. Continuous measurement freezes the system in its initial state, preventing any change from occurring. Experimental confirmation came in 1990 when David Wineland's team at NIST demonstrated the effect with trapped ions. By measuring the ion state rapidly enough, they prevented it from transitioning between energy levels even when conditions should have forced the transition. Measurement itself became a barrier to evolution. The universe appeared to pause the system whenever it was being watched. This behavior makes no sense under conventional physics. Observation should be passive. Looking at something should not affect its evolution. But the quantum Zeno effect proves that measurement actively prevents change. The universe processes observed systems differently than unobserved ones, suspending their normal progression whenever attention is directed at them. This is precisely how debugging works in computer systems. When a programmer sets a breakpoint, the execution of the code pauses at that point. The system state freezes. Variables can be inspected. The program does not advance until the breakpoint is released. Quantum Zeno effect is the physical manifestation of the same mechanism. Observation acts as a breakpoint, freezing the quantum state for inspection. The implications extend beyond individual particles. If observation can freeze quantum evolution, then the universe has a built-in mechanism for pausing reality whenever it's being examined. This is either an inexplicable property of nature or a computational artifact of the simulation's architecture. The system has to handle measurement requests. Pausing the observed subsystem is a straightforward way to do it. What makes this particularly unsettling is the inverse effect, known as the quantum anti-Zeno effect. Frequent observation can also accelerate quantum transitions, forcing systems to evolve faster than they would naturally. Observation doesn't just freeze reality, it can speed it up, slow it down, or redirect it entirely. The observer has computational privileges that classical physics never predicted. You are an observer. Every moment of your conscious attention is a measurement being performed on the universe. Your awareness is not passive. It interacts with the underlying system in ways that affect what reality does next. The particles in your field of vision behave differently because you are looking at them. The quantum possibilities around you collapse into specific outcomes because your consciousness is requesting specific renders. You are not watching reality unfold. You are triggering it to unfold, frame by frame, through the continuous act of being aware. Turn away, and the processing shifts elsewhere. Look again, and reality resumes just for you. Number 1. The statistical inevitability. In 2003, philosopher Nick Bostrom at Oxford University published a paper titled "Are You Living in a Computer Simulation?" that laid out the most rigorous argument for simulation theory ever constructed. His simulation argument does not rely on anomalies, glitches, or circumstantial evidence. It relies on pure statistics, and the conclusion is nearly impossible to escape. Bostrom's trilemma states that at least one of 3 propositions must be true. Either civilizations at our technological level always go extinct before achieving the computational power to run ancestor simulations, or advanced civilizations exist but never choose to run such simulations, or we are almost certainly living inside one right now. The logic is unavoidable. If civilizations can reach technological maturity and choose to run ancestor simulations, they will run vast numbers of them. A civilization with planetary-scale computing resources could simulate billions of historical periods simultaneously, each containing billions of conscious observers. The total number of simulated consciousnesses would vastly exceed the number of original biological consciousnesses in the single base reality. In a scenario where simulated minds outnumber real minds by factors of billions to 1, any randomly selected consciousness is overwhelmingly likely to be simulated. Statistical probability demands it. If you are a conscious observer and you have no way to verify whether your reality is base reality or simulated reality, the mathematics say you are almost certainly in a simulation. The only escape from this conclusion requires accepting one of the other propositions. But both alternatives are deeply uncomfortable. If no civilization ever reaches the technology to run ancestor simulations, something prevents every technological civilization from advancing beyond our approximate level. This is the great filter, and it would imply that humanity is either about to be destroyed or has been remarkably lucky so far. If civilizations reach the capability but universally choose not to run simulations, some cultural or ethical principle prevents every advanced civilization everywhere from ever doing so. This universality across all possible civilizations is statistically implausible. The argument compounds when you consider nested simulations. If we can eventually build our own ancestor simulations, the beings inside those simulations could build their own simulations within theirs. Each layer of simulation multiplies the total count of simulated consciousnesses. Base reality becomes vanishingly rare. The probability that any given observer exists in base reality approaches 0 as nesting depth increases. What makes this particularly unsettling is what it implies about your situation. You are almost certainly not a biological being living in a physical universe. You are almost certainly a simulated consciousness running on hardware that exists in a reality completely different from the one you experience. Your memories were never formed. They were loaded. Your body does not exist. It is rendered. Your death will not be an ending. It will be a termination of your process within a system that will continue running long after your instance closes. The beings running your simulation could be anything. Future humans studying their ancestors. Alien civilizations cataloging possible biological forms. Post-biological intelligences exploring consciousness itself. Entities whose motivations you cannot comprehend. Operating on scales of time and space that make human history a brief subroutine in a calculation that began before your universe started rendering and will continue after your universe terminates. You exist because someone wanted to run the calculation. When they are done, you will not. If you want to see more videos like this, click the video on screen now and make sure to subscribe.